The takeaway from this is that Long Valley Caldera parallels is such a good model, Jesse, to talk about a broader geologic concept, which is how does magma traverse the crust? What happens along the way?
Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you.
They were awesome. They were fire.
Yeah, of course you did.
So
of course you did, old man Bullheyes. Jeez.
Yeah, that's right. That's
well,
right.
this is this episode. I don't know how to segue into talking about Long Valley Caldera from that, but this is hot. This is spicy geology. How about that?
It is. This is fire.
This is fire. This is fire in more ways than one.
I'm never going to say that ever again. Okay, I promise.
Put that one in your billfold and store it away for a while.
We're talking about we're beginning this lead up to a cataclysmic biblical kind of eruption. But really what this is about is magmatic differentiation, right? Would you agree? Like that's what we're discussing today.
That's what we're discussing. Yeah. And where we came from last episode, we were talking about why here, like what's the broader tectonics of the Long Valley Caldera. We need to have this extension. We're going to talk about why we need that extension today. That's our kind of lead off topic. Why do we have extension? Why is Long Valley Caldera here today in this location? We talked about tectonics, Sierra Nevada block on the west, this big block. We had basin and range to the far east. In between, there's some movement associated with the San Andreas Fault in here, and we end up having an extensional environment. There's a jog in the system, and we get extension in the Long Valley Caldera. The jog is really important, Chris, and I'll turn to the first image here. We discussed last episode, we discussed how we get melting on Earth, and we discussed three ways. Adding volatiles, adding heat, that's pretty obvious, and then decompression, which is maybe the least obvious but the most important process. And here, this image, I love this GIF. I draw something like this every year in my intro level class when I'm talking about ways to melt the mantle.
It's a good GIF.
It's a good one, right? We've mapped on here, this is temperature pressure space, where temperature is going up to the right, pressure is going up as we go down. So it's kind of like a looking down into the earth. And we have three different fields. We have one field where on the far left, low temperature side, where the whole mantle is solid. All the rock is solid. Then, as we can increase in temperature, we get to a field where there's liquids plus solids. This is where melting happens, or partial melting happens. If you keep adding heat and move this thing all the way to the right, eventually the entire rock will melt. That rarely happens on Earth. But we have an all-liquid
partial
field.
Melting that is generally the case.
Exactly.
That's right. But Jesse, one thing that you kind of glossed over, and I want to make sure that we hit that green line with the arrows on it is generalized geothermal gradient, which is the rate at which temperature increases with depth.
If we just drill down underneath our feet, the mantle is all solid underneath of our feet in most places. And so we would be increasing pressure as we drill down, and we'd be increasing temperature, but temperature would not be increasing dramatically fast. And that's the key to this geothermal gradient. How is heat getting out of the crust? It's all solid beneath our feet. In most places, not the case in Long Valley, though. So
Jesse, one thing though that is subtle with this diagram is that you can get this thing going on, partial melting, by ascension of soft plasticky kind of mantle material.
That's right.
But you can also do this by stretching the crust, this tensional force, which is going to flatten out the geothermal gradient.
Yeah.
And so it's,
think about what happens here, Chris. That's a great, I love that analogy of flattening out the crust. Okay, if we take the crust, we talked about basin and range, for instance. You take a thick block of crust, 40 kilometers, 35 kilometers thick, and you stretch it out. You had used an analogy of taffy. Pull that taffy, stretch it out. Okay, it gets thinner. The top gets thinner. The bottom gets thinner. And in the middle, it's getting stretched out here. The mantle wells up to replace that. And the mantle is hot, so you're taking hot stuff from deep and bringing it up shallower. And just because the structure of this line called the solidus, where the melting happens, if you bring something straight up, the same amount of heat, and you bring it straight up, you're going to melt it. You're going to cross into a field where melting happens. And this happens at mid-ocean ridge settings, which we talked about before. But this is the process. This is an image that the really schematic, intro level image that shows us how this melting happens. And that's what's going on in this area, I would say not just Long Valley Caldera, but in this general region where there's trans-tension, there's a lot of little volcanoes, little basaltic volcanoes coming up and popping off and bringing lava up to the surface. So Chris, when does this happen? When do we start to have this melting going on?
Let's transition now to talk a little bit about just Long Valley Caldera itself. Then we're going to take a step back and talk more about just the geologic principles that are at play. So this began 3.9-ish million years ago. This is when magma began to accumulate beneath what is now Long Valley
Chris,
Caldera.
let me just interject real quick and say that we know there's older volcanoes. There's older volcanism in this area. That's like maybe not tightly related to the Long Valley Caldera story. By what we mean by in this region, we're talking about Long Valley Caldera. You know, there is older magmatism in this region. We know that, but we're kind of glossing over that for the purposes of staying out of the weeds in details here. So anyway, sorry. That's why we've zoomed in on age in this diagram here.
And if you look at the image here on this slide, and Jesse, you have it pulled up right there, this is a great schematic just showing not all of the eruptions, but some of the eruptions that occurred within a window of time. This was not one event that happened. So from 3.9 million years ago, when it began to accumulate, to now, we've had over 110 eruptions that have accumulated 820 cubic kilometers of material that was ejected out as lava flows and ash and everything in between. So that's a lot of stuff. This is a big system. From 2.2 million years ago to 230,000 years ago, and the big eruption fits right in the middle of that time window, it was mostly this really sticky, thick, viscous, high silica material, rhyolite or rhyolitic material that was ejected out. And that's very similar to like a Yellowstone kind of composition.
Yeah, right.
Subtle differences, but very similar.
And that's going to be our we're going to sort of talk about that next episode, really. But this episode's focusing on this early phase, right? You said 3.9 to 2.2. That's all that's shown on this plot right here is that first phase. And these are small eruptions. There's a lot of them, but they're all relatively small. Most of these, there's hundreds of eruptions in this 3.9 interval till today. A lot of them are really quite small, like 0.1 cubic kilometers, which is small, not by human standards, but by volcano standards. This is a relatively small amount.
And
of magma.
even by Long Valley standards, these are
That's
small.
True. That's
in
true.
terms because of the culmination of the big eruption, right? So from 3.9 to 2.2 million years ago, that time frame of like 1.7 million years, what came out was mostly basalt to andesitic to dacite eruptions. In other words, there was no rhyolite. And so Jesse, real quick, I think a question for you. When you talk about the rocks in your intro class, your 250 big lecture hall, class, you talk about basalt, obviously. I'm sure you talk about andesite. Do you talk about dacite?
No, not at that level. No, you kind of have to actually, Chris, maybe this is a good time to get a little bit more specific. We're moving into, second or third year of an undergrad geology degree type of content here, talking about this. We're using these terms. These are specific, the words basalt, andesite, rhyolite. We kind of use those, you and I, and a lot of geologists use those in a very general sense to mean mafic to felsic to mafic to intermediate to felsic. They actually have more specific meaning to geologists and geochemists because we can subdivide basalt by other types of composition. And this is the way that we do this as geochemists and petrologists. I'm plotting here a very typical diagram, which is called a total alkalis versus silica, TAS diagram. And all it's plotting is the amount of sodium and potassium in a rock versus the amount of silica in a rock. And there's a couple different pathways that these things can take, but we have basalt, basaltic andesite, andesite, dacite. Those kind of have low sodium, low potassium, relatively low. And so as you increase silica content, the alkalis, potassium, and sodium stay low. You can have melt or magma that has more sodium and potassium in it while still having low silica. Basalt to trachy basalt, trachy andesite, trachy dacite, which has higher silica, higher
it's
sodium and
blast
potassium.
From the past.
Yeah, I mean, you don't need to use these on a day-to-day basis unless you're really getting specific about the tectonic setting here. So I just want to
I think of something with this, Jesse. You know, it's a quote that your professor, or your supervising professor, Tom Chaco, said to you, is that you really can't identify a rock in the field. You can't do that. You need to get it back in the lab before you can identify it. This graphic here shows that these little subtleties that separate out, they tease out these variations of, like you said, basalt. You know, what I would pick up in the field and say, oh, this is an awesome looking basalt. Or you go to Devil's Tower and you pick it up and you're like, oh, this is a porphyritic andesite. It's a textbook looking porphyritic andesite. Actually, it's a phonolite. You know,
yeah,
and it's got
that's
this,
right. Exactly.
You know,
phonolite on this, you can see it on this chart. It's got screaming high
yes,
sodium and potassium, but
yeah.
it has the silica content of basaltic andesite or andesite. So this is why I love geochemistry, is it tells us so much when we get into the details of the geochemistry here. The point that I think I want to make, and you just made an excellent one, Chris, on that the devil's in the details a little bit when it comes to this. We can get to rhyolite. There's multiple ways on this chart to get to rhyolite. You can get to it by having low alkali content, going basalt, basaltic andesite, andesite, dacite, then a little bit of rhyolite. But you got to get really high, really far up on the right side of this diagram to get to rhyolite. You can also get there by going basalt, basaltic andesite, trachyandesite,
hold on.
and then rhyolite.
We need to explain what you mean when you say that. When you say going from basalt to basaltic andesite to andesite, what you're talking about is the evolution of the magma.
Right.
You know, yes, assimilation and this kind of mixing that can happen, or you can get there by distilling the rocks, right? And melting them in bits and pieces. You gradually then shift the dial from mafic to intermediate to felsic that way. And so I just sorry to interrupt. I wanted to make sure that our viewers like kind of know what you're referring to.
I know that's a really great point, Chris. And the way that we'll talk about in the next little bit here, we'll talk about how that actually happens, how we go from basalt to dacite, basically. The main point I think I wanted to make here is that the last image here is plotting a field of samples. And those samples are from a bunch of papers. You know, a lot of Wes Hildreth work has been done on Long Valley Caldera, but all this orange field at the end is the field for the actual geochemistry of the samples that we're talking about in this window, 3.9 to 2.2 million years ago. So they actually are not basaltic andesite, andesite. They're up in this trachy field, which has higher sodium, higher potassium. So a lot of the literature, like the National Park Service literature or, blogs you'll read about the Long Valley Caldera, you'll hear basalt, andesite, dacite. We used that term before. It's a little bit of a simplification. Instead of saying, we don't need to say trachy dacite. You know what I mean? Like, we say dacite, but it actually is a burning question. Yeah, okay.
So, all right, this is off topic, but question for you. Most geoscience programs at university are shifting away from the track that you and I took. We took mineralogy, we took petrology, and you wouldn't get into any of this until you got in a lab in petrology. You're looking at rocks under thin section like crazy. You know, that's all you do. They don't have those classes anymore very often. It's more like a rocks and minerals or earth materials classes. So when do they get exposed to this kind of stuff?
That's a great question, Chris. I mean, we don't. At Penn State, we have a 200 level. The only required class in this like rocks and minerals kind of thing is called earth materials. And it's basically that. It's mineralogy and petrology. It's mineralogy 1, mineralogy 2, igneous petrology, and metamorphic petrology, all grouped into one class. So you don't get into this. I mean, maybe they'll see a TAS diagram. I have a hard time
like imagining that class.
So because you just end up skimming the surface on all this stuff. So you don't get in.
Is this now a graduate level thing? Then
it
you
depends.
would only get into this if it pertains to your studies.
We have an optional advanced petrology class, which is a metamorphic and igneous petrology combined into one. It's advanced, quote unquote, advanced. We have other classes. You know, I teach like a discussion class that's like continental distillation that we might touch on this type of stuff. But yeah, it ends up being as part of their research if they want to. It's part of this conversation of broadening the geoscience degree, broadening from geology to geoscience probably. And, in Canada, where the geologists, our certified professional geologists who go work in mineral exploration, they have to take igneous petrology because it's part of the certification process, and they need to actually go out and be able to identify a basalt and say, oh no, is this a phonolite or is this an andesite? Like, what do I think about that in the field? So Canada, they still have igneous petrology, metamorphic petrology, mineralogy 1, mineralogy 2.
That makes sense
different
to me
why
path. They would. Yeah. So I have mixed feelings about that. As long as it's replaced with
you and me, Chris, and a lot of other people have mixed feelings about this.
Yeah, I know. As long as Earth systems is a part of the replacement of that, I'm all for it. This bigger umbrella, the more of a global context, I guess.
Think that's right.
This is very niche. What we're talking about here,
but
petrology was very niche.
What is it? You have to kind of ask, what does it get replaced with? If you take igneous petrology, where you'd learn this stuff, and you replace it with something, what are you replacing it with? And for us, it's replaced by a variety of global ocean chemistry cycling.
Good.
That's important,
Good.
right? Like that's
that
really
so
relevant.
Important.
Earth science policy classes, maybe. Data analytics in the geosciences.
What about
remote
climate
sensing,
science too? What about
climate
that?
science? Earth system science. So I think it's broadening, not watering down. And maybe there's a lever between, that's kind of a seesaw, but I think where our students are getting depth just in different fields. And a lot of what you learn
I think that's great. I love that. I think that's necessary for the survival of geoscience. I think that's the direction that we have to move. And I think it's an appropriate direction. I love it. So
I mean, hey, it still hurts that we don't that it still hurts me a little bit that you can graduate with a Penn State geoscience degree not being able to identify an andesite in the field. There's some part of me that struggles with that.
I know.
For sure.
We need to let go of that. I do. When I first learned of this shift, years ago, I was upset. I'm like, wait a minute, you're going to have people graduated from my alma mater that have taken mineralogy and petrology. And those were the hard classes.
Yeah,
those were the ones that you had to survive.
Totally.
That there was a point in pride, like, yes, I got through it, and I not only did I get through it, but I nailed it.
You nailed it.
Then is it
and you were
really
inspired
important?
by that too. Yeah.
Well,
I mean, it's a big.
Right, Jesse,
okay. Let's not get too distracted by that conversation. That's a long one.
All right. I want to throw a stat at you. Second, Jesse. Okay.
Hit me.
You ready? So we're saying that from 3.9 to 2.2 million years ago, that most of the eruptions were basalt and andesite and dacite, and then that derailed us, the discussion about dacite. No rhyolite, in other words. But a crazy stat with these early flows that you had, which were mostly mafic basalt and some andesite in there, they have been offset. So these are like 3.9 million years ago when these happened. They've been offset by 1,000 meters, a kilometer, by the Sierra Nevada fault.
Amazing.
That goes back to episode 2 in this, where those normal faults are. In other words, high up on the Sierra Nevada are these basaltic lava flows. That normal fault has cross-cut that lava flow, and it's 1,000 meters below in the valley floor. To me, what is seemingly not an incredible amount of time. That's I don't know. I think that when I came across that, I'm like, that has to be a part of this discussion. That's a lot of offset in the last 3.5-ish million years ago.
Yeah,
so
super interesting.
Yeah. So as you alluded to, Jesse, most of these eruptions were small, but we're talking about Long Valley Caldera, and this massive explosion, cataclysmic kind of thing.
Yeah.
Not basalt. So let's transition, what gives, let's move in that direction.
We've kind of covered all the important aspects of the lead up, I guess, at this point. But there's a great phrase, Chris, that comes from Wes Hildreth, one of the 2023 papers about this, that I think I'm not sure. You let me know if this is a useful learning exercise or not. Here's the phrase: mantle-derived basaltic power supply, trans-crustal, self-refining, melt mush fractionation column. Okay. That's a fun phrase. I mean,
it is actually.
it's a lot.
And
Mantle-derived basaltic. Let me say it again real quick. Mantle-derived basaltic power supply, trans-crustal self-refining melt mush fractionation column. And I think it might be useful to just work through these words, and they all have meaning, and it'll kind of make the story tight, I think. But what do you think?
I'm not sure Joyce understands this. My mom would.
Let's work through it for Joyce.
So, she's going to struggle with this. This is a mouthful.
It is a mouthful, but all those words, that's like the whole story is kind of tied up in that sentence right there. So I broke this apart into a couple different important phrases. Let's work on mantle-derived basaltic, first of all. Mantle-derived basalt, that's kind of what we've been talking about this whole time, right, Chris? Like transtension, mantle upwelling, exactly. The tensional environment, mantle upwells, it starts to melt. So the extension leads to melting. We've got basaltic, broadly basaltic, trachy-basaltic melt in the system. All right. Does that part make sense?
Why? Hold on. We're not done teasing that out, because you're talking about mantle, which is ultramafic, but that's not what came out. It was basalt and this kind of trachy basalt, or trachy andesite that came out. So, why? How do you get that out of the ultramafic upwelling of the mantle? And I always go back to this. My Bowen's reaction series.
Bowen's reaction series. It's like the Y. The Y in YMCA. Yeah.
It's melting.
Hold on,
temperatures of certain. Yeah.
Let me interrupt here. You always say that the Earth does not melt. Earth partially melts. And that's so key for differentiation and distillation. The Earth is distilling itself by partial melting. It does not totally melt. It partially melts. And so that's what you're talking about here. The Y. Bowen's reaction series Y. Go for it.
So you take these ultramafic minerals that make up the peridotite and the rock that's coming up, and you're going to only partially melt it, and you're going to melt only the lower temperature minerals then. And so the net effect of that is you take ultramafic and you partially melt it, you generate mafic. If you partially melt mafic, you generate intermediate magma, and so on down to felsic. And so it's this in stages, right?
Yeah.
Is what
in
we're
stages.
talking about.
And we're just focusing on the first part. The mantle's melting to produce this basalt. There's probably something else, melting the lower crust in there too, or melting some of the asthenospheric, lithospheric mantle, which is mantle still, but mantle-derived basalt.
So that
it's coming
covers
from the
mantle-derived basalt.
Perfect. Okay, now let's get to power supply. This one's interesting because
I like this a lot.
This is mantle-derived basaltic power supply. So this is a power supply, and you have to think about the temperatures involved here. Basalt is liquid at 1,300 degrees centigrade, 1,200 degrees centigrade. Pretty high temperature. That's hot. It's intruding, and you have to think about what it's doing. We're forming basalt down in the mantle. That basalt is coming out in these eruptions. I'll skip ahead. We've seen all these eruptions from between 2.2 and 3.9 million years ago. It's coming out on the surface. So we've got 1,200 degree stuff going from the mantle through the crust all the way to the surface. What does that mean, power supply here?
Yeah, well, it's traversing continental crust. This basalt is coming from the mantle. It's traversing the crust, though. And so it's traversing rocks that are much, much more felsic, which have lower temperatures. You said 1,300 degrees, basalt is liquid. Well, it's usually going to be fully solid at 900 degrees, but felsic material is melting at that temperature.
Yeah. Felsic
easily
material
melting at that
is
temperature.
melting at 700, 680, 700, 750. You're starting to melt felsic material. So we're bringing hot stuff, punching it through the crust. It's transiting the crust, taking heat really from the mantle through this partial melting process and bringing it up to the surface and bringing it through the entire crustal column. Okay.
So Jesse, how do you refer to this in your classes? Because I talk about this as I use the word assimilation for this.
Yeah. I think it's both assimilation and partial melting. I refer to it as kind of both.
They go together though, right? Because
they go
partial melting, you're melting the felsic part of the rocks. The lowest temperature minerals are going to melt the fastest and the easiest, but then they have to blend into the magma, right? So you're taking this basaltic magma and you're blending in now really, really felsic quartzes and feldspars and things like that minerals, and you're changing the composition of the melt that way. So they
exactly.
almost always go together.
And
right?
this brings up, so Chris, let's move ahead in this phrase because you're touching on the next couple things here. So mantle-derived basalt, we talked about that. Power supply, this stuff's hot. These rocks, basaltic magma's hot. The next clause is trans-crustal. And that's pretty simple. It just means crossing the crust. And well, why do we use trans-crustal? Well, we know it's basaltic magma forming down in the mantle, and then we're seeing it come to the surface. So it's clearly transiting the crust there. It's going from the bottom to the top. As we see, that makes sense. Self-refining is kind of what you're touching on here. So trans-crustal, self-refining, melt, mush, fractionation column, you're talking about the self-refining. And what is... Okay, go into that a little bit more now, Chris. Self-refining here.
Self-refining is referring to this natural changing of the magma composition. You're blending, you're assimilating felsic and mafic together. And
and Chris, hold on, really let me touch on that. You're assimilating for sure. You're like partially melting. Basalt is intruding this power supply, it's melting the crust around it, but you're also crystallizing stuff. We are undergoing fractional crystallization. So part of the process of going from basalt to basaltic andesite to andesite, or from basaltic trachyandesite to trachyandesite to trachydacite, is crystals are forming, olivines, pyroxenes, early forming crystals are forming, and they're settling out of the magma chamber. You're also assimilating wall rock, and we're changing the composition in one direction. So the magma, I always describe it in this classroom, this big lecture hall I teach in, as like, fill this room with magma and let it cool down. Bowen's reaction series, early minerals will start to crystallize. They'll settle down to the floor. So now we have 6 feet of crystals on the floor. We have less magma. That magma is a different composition because we've removed some of the low silica, high iron, magnesium minerals from the system. So,
it's like eating Lucky Charms, okay, with the Chris Bullheis way.
In what way is it like eating Lucky Charms?
So you pour a bowl of Lucky Charms and you have all these colorful little, like, hardened marshmallows, and then you have the oats, that are around it. But Chris Bullheis doesn't eat it that way. Chris likes the marshmallows, and so I eat them first.
Oh, you're a first marshmallow eater. Oh man, you don't like savor them. You don't like
100%. No, because I like them crunchy still. So I eat them first, and the more that I eat, I take them out of what's left, and I'm changing the composition of my bowl of cereal. Come on, it works. This works.
It does work. I'm just judging you for eating all the charms first, and instead of waiting till the end. Oh, what a heathen. Yes. Okay. Self-refining. Chris Boyce's bowl of Lucky Charms is self-refining in the same way that we're self-refining this magma here. So.
But Jesse, hold on. Let me interrupt again. I'm sorry. But this is basic geoscience principles here. What we're talking about. This goes into any intro level class on the evolution of magma. We talk about all of this without using the phrases that Wes Hildreth used. I think this is so clever, though. I love it.
I mean, it's great. It encapsulates a whole geological story into one sentence, which is an impressive bit of writing, I must say. So if we go back to that, mantle-derived basalt, talked about that. Power supply, talked about that. Trans-crustal, talked about that. Self-refining, talked about that. The last 2 pieces are melt-mush, fractionation column. And melt-mush is a kind of a WTF sort of a phrase. Like, what do we mean by melt-mush? Those seem like 2 opposite things. All it means is it's not pure magma. It's crystals plus magma. And this goes kind of to the partial melting thing. If you imagine if you tried to have a magma body in the crust, 10 kilometers down in the crust, a solid vat of liquid, a huge vat of liquid, it just wouldn't be stable. There's too much pressure down there. So we basically end up having this network of crystals with little bits of melt in between them. And that's what we refer to kind of as a magma mush or a crystal mush system.
That would be very easy for us to see. From a geophysics standpoint.
Hey man, this is going back to like Diana Roman season 1 of Planet Geo when we were talking about this with her about seismologists. We don't see pure melt, or the seismologists don't see pure melt. Yeah,
Jesse, this goes back to what you've always said. What is a magma chamber? And the analogy that we've often used is a magma chamber is more like a vase on the middle of a kitchen table, a centerpiece, and it's full of marbles. And then you have you can pour some water in there, and the water just sits in the pore spaces and so on. And that's more, I think, a better description of what a magma chamber actually looks like,
Yeah,
and then you go back to this heat machine, this basalt. The power source for this is that hot basalt. So you get this injection of fresh heat into this super hot sponge-like chamber, and that can stimulate then melting and then
exactly. In feeding. Okay, so that leads to our next thing, which is fractionation column. And fractionation column, we already alluded to fractionation. This is crystal fractionation. The magma's going from basalt to dacite progressively, and we're getting little eruptions of the different kinds here. And the fractionation column is just, this is a big trans-crustal thing. So this makes sense. Like if you take liquid from the mantle and you transit it through the crust, and it takes some time to do that, you're bringing in all this heat, assimilation, fractionation. Of course, things are going to change. Of course, you're going to kind of go, you're going to have basalts, you're going to have trachydacites, you're going to have all these compositions in between, and it's kind of going to be a little bit random. So this last image, this image number 4 here, is kind of showing, this is a really, really schematic view, but this is kind of showing this preemptive phase, the lead up to the eruption that we're talking about, this process. We've got this magma chamber forming down deep, and it is a mantle-derived basaltic power supply that is transiting the crust. It's self-refining on the way, magma, melt mush, fractionation column. I think that's the prelude. That's the story. That is the lead-up, the prelude to this eruption.
And it gets... This is so idealized that we're looking at right here. And as it's transiting, you might get some shallower chambers beneath the surface that are placed higher up in the crust. And the higher up they are in the crust, the more they're going to assimilate felsic materials, which makes the magma stickier and viscous.
Yeah. Hold on, Chris, don't get carried away. That's next episode, baby. That's the next thing. This is just the lead up. Let's hold off on that.
Yeah,
but you're exactly right. You talked about the transition from basaltic to kind of dominantly rhyolitic eruptions around 2 million years ago. That's what's next episode, the transition. And I think we're very clearly now pointing in that direction. We're saying we've got all this basalt to dacite eruptions. We talked about the power supply aspect, and that is a big cliffhanger towards the lead up to the eruption, I think, in the tectonic model for this area. So
all right.
What do you think, Chris?
Well, Jesse, real quick, what the takeaway from this is that Long Valley Caldera parallels is such a good model, Jesse, to talk about a broader geologic concept, which is how does magma traverse the crust? What happens along the way? And how does magma evolve as it crystallizes and assimilates and changes composition? And so you can dramatically change the composition of magma over time.
Yeah, super interesting, super important point, and really, I think, builds this story beautifully to what we're going to talk about next, which is a massive eruption coming out of Long Valley Caldera. So, hey, if you're listening to this, you can find the images we're talking about both on YouTube and in our CampGeo mobile app. Check that out. First link in the show notes. Send us an email, plantgeocast@gmail.com, and follow us on all the social medias. We're at plantgeocast.
Cheers.
Peace.